network and deep learning. So as you know that basically the deep learning networks have basically revolutionized different fields. So we will be understanding some sort of theoretical aspects, and also we will be doing some sort of demonstration. Okay, so let me first share the screen. Before that, it would be good if the participants they can give a brief introduction of themselves, so that I will be able to understand from their background and what they want to learn from this talk. Yes, so participants, you can start introducing yourself briefly.
Any of the participants, please introduce yourself.
Hello. Hello. Am I audible?
Yes, yes, you can
Yeah, I'm Dr.
proceed.
Yasser. I'm actually an assistant professor here in VIT Vellore. So I basically work on materials related work only, mostly on mechanical behavior. And as far as what I'm expecting from this workshop or in this session would be like I am actually trying to start using machine learning. So like what I would like to see is how how as a person like me to get started with machine learning, how we can use different machine learning tools. Because I don't want to start writing a code from the scratch, but I would rather want to use existing codes to apply to my problems, research problems. So some kind of hands-on demonstration or something like that.
Okay, good.
Thank you.
Yes, Mohammad Furkan, I think you have raised your hand.
Hello, am I audible, sir?
Yes, yes,
Hello,
yes,
am I audible,
yes, you
sir?
are audible. Yeah, yeah. Please
Yeah,
continue.
myself Furkan Ansari, PhD student from IIT Jodhpur. Actually, currently I'm working on alloy design and development based on certain alloy design parameters. So currently I'm also focusing on machine learning to design and develop and to predict the mechanical properties like strength, elongation, tensile properties. So currently I'm working on this area. So I have various input parameters. That means I have data set, but I'm learning to machine. I'm learning basically how
Okay,
to
okay, then understood.
generate this prediction like mechanical properties.
Mhm.
Yes.
Okay, then maybe I can start the presentation. Okay, can you see the PPT?
Yes, sir. Sir, your voice is not audible, sir. Please.
Hello, yeah. Okay, now
Yes,
the voice is audible?
sir.
Yes. Okay, okay. So first of all, we are going to have some basic introduction to neural networks and deep learning. So when we are talking about machine learning, so machine learning involves some sort of a learning. So learning is different from kind of rule-based formulation, where basically we basically try to understand the phenomenon using three types of learning methods. One is supervised, unsupervised, and reinforcement learning. So first of all, we have to have some idea about these different types of learning methods. In supervised learning, what happens is that some labels are given for the training samples. For example, I can say that look, this is an image of an apple, this is an image of an banana. So this kind of label. For example, let's say that there are some emails. Okay, so the emails can be classified as readable emails or spam emails. So this constitutes the training samples. Once the learning algorithm has a sufficient number of training samples, the specific features, and then it can perform the classification or other supervised learning task. Okay, then there is this kind of unsupervised learning. In case of unsupervised learning, we don't have any training samples as such. Rather, the learning algorithm itself understands some patterns or some characteristic from the data without any supervision. For example, clustering is an example of unsupervised learning. So here the similar data points are basically grouped together. And there's another type of learning. This is the reinforcement learning. So in the case of reinforcement learning, the agents basically interact with the environment, and the environment gives some feedback or some reward. Based on this feedback and reward, they take their next step. Okay. For example, in many games, basically you see that in many video games, you go there, you do take some action, and then you get some points or some rewards like that. So this is an example of reinforcement learning. For example, we have shown that this classification task. So let's say that there is a text and you have to classify these text into either class A or class B or somewhat something else. So this is a classification which is a supervised learning. Again, it can be a task of anomaly detection, sequence labeling. So these are examples of supervised learning. Also, the supervised learning can be this is problem called regression problem. It is also an example of supervised learning. So here, what is the problem? Here you have two values, x values, some points. You have two coordinates x and y. For some examples, you know that if the x y value is this, y value is this. For some unknown examples, you have to compute the value of y given the value of x. Okay, so that is a functional mapping kind of thing. So in that case, you see that these dots are actually given. So that means that you know that what should be the y value corresponding to these x values. So for unknown x values, you have to simply predict what should be the y value. For example, this clustering task, this is actually unsupervised task. Here you see that the different colors points are basically grouped together. So that means similar points are grouped in a similar cluster. Okay. Now, some of you must have done some work on machine learning or even deep learning. Now we have to understand how this deep learning is different from machine learning. In traditional machine learning framework, you have some input data, and some features are extracted from the input, and then it is fed to some classification algorithm. So it may not always be classification, let's say some learning algorithm, and the learning algorithm gives you some prediction. Here this is a classification problem. It predicts whether it's a card or no card. Okay, here what we are doing is that we are giving you, we are basically telling the algorithm that look, you extract these features. So for cars, the feature may be the number of wheels, or maybe the shape, or maybe the size. These are the features. But in case of deep learning, we simply feed the input data to the learning algorithm, and the learning algorithm comes up with a prediction. Okay, so here basically we don't explicitly mention about any levels as such or any features as such, because you see that in this case the features may be easy, but there are many kind of the types of data where you cannot tell that this should be the features, isn't it? So that is why the deep learning algorithm is preferred nowadays. So you see, when we talk about the field of AI, this machine learning is a subfield of artificial intelligence, and deep learning is another subset of machine learning. Okay, so and all comes under the bracket of artificial intelligence. Okay, so the machine learning methods are subfield of learning representation of data. They are more concerned about that rather than the feature extraction. And also deep learning method algorithms attempt to learn multiple level of introduction by using hierarchy or multiple layers. Okay, so here you have a kind of deep network, and this deep network is able to learn the good representation for performing the prediction. Okay, now mostly we have seen that in many practical application the features are not understanding these features may not be very easy. Okay, for example, if I tell you that how do you recognize your friend, the face of your friend, I give you 100 facial images and you can easily identify which one is your friend Ramesh or something. Okay, but if I ask you that how do you know that this is Ramesh's face? What are the features? You cannot say, but you can easily identify. So the features are not very easy to identify and is very complex and complicated. So the learned features are very easy to adopt, fast to learn. Okay, so the neural networks can understand these features. So deep learning provides a very flexible and universal way to represent all kind of data. Now sometimes you may say that image data might be easier, but there are other types of data like sensor data, then speech data, other kind of text data which are very difficult to understand. So we are mostly concerned about nowadays deep learning methods are used. So it can use both for unsupervised learning as well as supervised learning. So mostly these networks use end-to-end kind of learning. If you saw the Google Trends that previously we had less amount of computation, so mostly there was not much kind of improvement implementation of deep learning in the 2000 early 2000s or so. But after the 2013 or 15, so most companies and academia they are adopting deep learning for diverse set of problems. And one particular usefulness of machine learning or deep learning is that it can be used in many applications, whether the application is biomedical or metallurgy or mechanical or let's say that computer vision. If you are able to formulate the problem in machine learning, you will be able to get a good solution. Okay, now most of you are concerned about image processing also. So when we are talking about an image, okay, what computer sees is a number. Okay, so for example, this number it is actually a matrix, or if you consider the RGB image, it is actually a 3D matrix or 3D array. Is of size, let's say 800 into 600 into 3. So if we want to classify this image, so how can we do that? Okay, let's say that we have four classes. So we have to understand whether it's a cat or dog or truck or plane. So we feed this image to the classification algorithm and they give you the prediction. But the image is actually a matrix, okay, between the number 0 to 255. So when we perform the classification, we first of all can look at low level features like the lines and edges you see, or maybe mid level features like this kind of structure of eye, nose and ears, or maybe we can have some kind of very high level features like you see that here some of the faces are it's these images they reflect some of the facial images, isn't it? But what kind of feature we are looking for, that depends on the input data. and we are not always sure. Okay, so basically we are trying to use this deep neural network to identify these kind of features. Now we will try to see that how these deep neural networks or artificial neural networks actually learn. For example, let's say I have this image I want to classify. I am going to use a linear classifier. Okay, so here x represents the image, and we have a parameter w and b. Okay, we choose an initial value of w, and we get a value of fxw, isn't it? Now, depending on the SXW, we take a decision that whether this image belongs to cat or dog or something. Now, if we want to go like this, we have to select the optimal values of W and B, isn't it? And the function f also. So, what we do is that in case of supervised learning, we give you a number of samples, okay, training samples. For this, we know that the what should be the fxw, and depending on that, we select the values of w and b. If the number of training samples are sufficient, mostly we get a fairly good result. Okay, but this classification, so you see how this works. So first of all, we have this image, so which is as a x is a matrix. You multiply it with another matrix w, and you add it with this term b. Okay, finally you get this kind of score, and you apply a function f, okay, which is an activation function. So you get this score. Depending on this score, the learning algorithm classifies whether it's a cat or dog or sheep, or the classes. Okay, but the main problem is that you do not know what should be the actual value of w and b. So the values of w and b are learned from examples using supervised learning. So for example, give you 100 cat images. For these cat images, I know that this is a cat, so I give the scores accordingly, isn't it? Similarly, I have 200 dog images or 500 sheep images, like that, so I know what should be the score. So the cat score in this case should be 100 or something like that. Okay, so because of I know the training sample, so I tune the parameters w accordingly, so that my training samples are actually classified, are correctly classified. Now when I give an unknown image, I have set the parameters w and b, I get a prediction, and this prediction is actually often correct if my classifier is good, of course. Okay, so this example shows how the supervised learning basically works, or some parametric supervised machine learning algorithm works. Okay, now here we are using only a linear classifier. So that means that the class boundary is linear. This class boundary is that, let's say that how the car images are separated by the cat images. Okay, there is a kind of distinct boundary. So this boundary, we consider that this boundary is actually linear. So the problem is that in real examples, the boundary may not be very linear. Okay, so this is just a basic kind of classification algorithm. For example, let's say that we have a problem here. There are two classes. The blue color represent class 1 and the red color represent class 2. So you see that the classification boundary is not always linear. Okay, so the linear classifier does not work always. So what should we do? For example, you see that in this case, the classes are not linearly separable. Okay, so what we want is that we want to approximate this kind of nonlinear decision boundary, isn't it? But can anyone tell me that how can I represent this nonlinear boundary? Is there any formula to represent this nonlinear boundary? What do you think? For example, what I am saying is that in case of decision boundary, I uh, know that what is the formula of this state line, isn't it? What is the equation of the state line? But if my classes are not linearly separable, let's say that the decision boundary looks like this in this image. So can you write a formula for this decision boundary? What do you think? If I can write the formula, it's fair and simple, isn't it? I have the coordinates, and depending on the value of the function, I will decide whether it's represent class 1 or class 2. So how should we go forward? Any comments? Yes. You see that this decision boundary is very difficult to represent with any equation, whether that be a polynomial or something like that. So maybe, but we can represent some sections of the decision boundary using some formula, isn't it? So the neural network actually does that only. It identifies the decision boundary. Some neurons or some layers identify some portions of the decision boundary, isn't it? For example, you can see that this lower area, so it represent kind of a parabolic thing, isn't it? The other portions represent other functions. Okay, so that is why the neural network is better than the basic classifier like decision boundary and linear classifiers. Okay. Now, people thought that our human brains, it is actually a very powerful machine. Okay, so it can identify patterns, it can recognize facts. So how does it do that? So people started studying the human brain. Okay, so what happens in a human brain is that they have a kind of different type, a huge collection of neurons. So these neurons collect signal from other cells through a kind of structure called dendrites, and then they have a action and which actually passes this kind of information. So they form a kind of network. So researchers thought that if the human mind is very much powerful to perform this kind of pattern classification task, why don't we try to replicate this human mind? Okay, so that's why neural networks were born. Okay, so a neural network basically mimics the human brain or the neurons. Okay, so a neuron basically receives a excitation input from different kind of streams, and it combines, aggregates this kind of information and performs an threshold function or some kind of activation function. Okay, so then it passes this information as the output. So you can see that you can consider these three as the inputs to the neural network, and the inputs are basically summed by or performed by a weighted summation. Then an activation function is used to get the output. Okay, so this is how they tried to develop the electrical equivalent model of a neuron, so that it can learn different kind of patterns very easily. So here you see that x1, x2 to xn, these are the inputs to the simple neuron, and this neuron sums up the inputs and then takes some kind of action on that summed out input. Okay, so here also we use the concept of training and testing. In the training phase, what happens is that the neural network uses the training samples to learn the optimal value of the weights and the bias and the other terms, so that it can perform accurate prediction on the unknown samples or the test samples. Okay, for example, let's say that you have 5,000 images. You want to classify, so you can use 60% of these images as training samples, and the rest 40% samples can be used for test samples. So the model is basically specified, or the parameters of the model are computed as per this 60% training samples. And then the model is called the trained model, and the trained model can be used to perform prediction on the rest of 40% samples. Okay, so that is why the supervised learning, how the supervised learning works. So is it clear? Or if you have any doubt whatsoever, you can anytime ask questions. Okay, so these neural networks in the training phase can be trained to fire or not based on a particular pattern. So if they receive some kind of input pattern, they can, tend to fire. Okay, so that means they are sensitive to a particular type of features. So in the training mode, when a taught input is in the testing mode, when the testing input pattern is detected in the input, its associated output becomes the current output. So that means it becomes activated. So you have a large number of neurons, and it is connected in a kind of grid like structure. It has many layers, so that a particular layer or a particular neuron is actually specific to a particular pattern. Okay, so whenever this pattern comes, this kind of neuron fires. So that's how the neural network has a lot of flexibility, and basically they can identify many types of input pattern and do the prediction very accurately. Okay, so that's a basic overview of the neural network. So once again, I will try to repeat. So there are the different inputs, and these inputs are summed by some weighted fashion, and there is some activation function which is operated on, and they get you the output. Okay, so in case of supervised samples, you know that if this the input is this, the output level is this. So according to that, you compute the kind of weights, and then you use it for the testing phase. Okay. Now, deep neural network is basically a collection of neural networks. Is actually in deep neural networks we have a large number of layers and a large number of neurons in that kind of individual layers, so that we can extract a lot of features, isn't it? Now the question is that this idea was around for a long time. Okay, so people had this idea for some time now, but they were not able to implement this deep learning. Okay, so this is mostly because that we did not have a lot of data at that time, or also we did not have powerful processing facility, and also there were not dedicated softwares. You have to write the codes on your own, everything from scratch, so it had a lot of difficulty. But after I think the 2010s or early 2000s, the things began to change. We nowadays we are getting a lot of data, whether it's a image data or some sensor data. Everything is available in internet, even free, so we can train the networks very easily, and and then we have the kind of massive GPUs and parallel processing facilities, so that we can deploy a heavy models. Okay. So the deep neural networks, they actually use these neural networks with several layers or modules. So these layers and modules form kind of nonlinear, hierarchical and abstract representation of the data, and they can approximate very complex function between input and output. So I forgot to mention that whether it's a classification task or a regression task, the main mathematical formulation is a kind of functional mapping. So for example, a regression task is basically a mapping between y and x, isn't it? In a regression, we have some kind of training data where we specify that if x value is this, y value should be this, like that. So for unknown points, for unknown x values, you have to predict the y value, isn't it? So the ultimately the problem is a mapping of the variable y and x. So you have to represent y in terms of x. Okay. And in case of classification, it is also same. So in case of classification, the value of y is not a kind of continuous value, rather it's a discrete value. For example, let's say you have 5 classes. So y may be 1, 2, 3, 4, 5 only. These are the values. So y cannot be 1.5, 1.25 or something. So you have a distinct number of values on y. But still, this classification problem is also a kind of functional approximation problem, isn't it? But there are basically huge, very famous mathematical proofs that showed that these neural networks can uh, approximate, represent a very complex models. Okay, so that's why people thought that why not use this for this kind of classification, regression, clustering, and other tasks. So nowadays that if deep learning models are used in computer vision, speech processing, data generation, even text and natural language processing, and many other fields. Okay. So now let's take an example how deep learning methods are used in some applications. Let's say that I want to classify handwritten digits. So you there are basically 10 classes from 0 to 9. Okay. So let's say that you have 10,000 images, 10,000 handwritten images, and you want to classify this. So we have a kind of we arrange the images as pixels. Okay, so let's say that this is only a binary image, so that means you can have two values, 0 or basically 1. Now you pass these images to the machine learning algorithm and you get the class output. So the class output can be class 1, class 2 or class 10. Okay. So here basically what we are doing is that we are mapping this input data to these output classes. So let's say that it can have 256 values. So there are 256 values for each image, and you have to represent it as a either of these 10 values. So this is how why this is actually a functional mapping kind of thing. Okay. So the deep learning method, what it does is that it identifies the function f that maps the input to the output. Okay. Now this is what I was talking about. So here basically we have the inputs a1, a2 to ak. Now the individual nodes of the neural network, they basically perform this operation. So they perform the weighted sum of the inputs, and then a bias term b is added, and finally this z value is actually passed to an activation function, and basically we get some output. Now if you observe this term z term, it is nothing but a linear combination. So it represents the linear classification boundary, isn't it? That is showed here. But the actual decision boundary is non-linear. So how do we get that? So for that reason, we use this activation function, which is nothing but a non-linear function. Okay, so that we get kind of non-linearity in the data. Now, what kind of non-linearity we will talk about that. So in case of neural network, we have let's say 5 layers or L number of layers. We arrange it like this. Okay. So you see that the output of layer 1 goes to layer 2, the different nodes in the layer 2. Similarly, the output of layer 2 goes to the different nodes of layer 3 like that. And finally, let's say we have every node, what they have this weights W1 to Wk, and it has this bias term. Okay. So when we are talking about tuning this neural network, so we are talking about selecting the optimal values of these weights and these biases. Is it clear? So that's this is very important concept. Okay, so often you hear about the term of that training a neural network or tuning a neural network. So it means that you have to select the values of W1, W2, these weights and this bias term. Okay. So in case of supervised learning, what happens is that I know the input and I know that what should be the corresponding output. Okay, for example, that I give an image of this class 1. Okay, I know that this is class 1, so that the output y1 should be higher than y2, y3, ym like that. And ideally, output y1 should be 1, other value should be 0. Often this output, it represents the probability of the class. Okay. For that reason, the output should be 1 0 0 0 like that. Okay. But let's say that I choose any random kind of weights and bias, so I will not get this value. I will get some other value. Okay. For other training samples also there will be different values. So what I try to do is that the network tries to do is that they compute some sort of error. Okay, what does the error mean? The error basically means that what is the difference between the actual output and the ideal output. This is called the loss function. Okay, and this loss function is computed every time the neural network weights are updated. Okay, so also the next slide will clarify this thing. For example, let's say that I have this input 1 and -1, and I use 3-layer neural network, and the weights are like this 1 -2 -1 1. So what happens here, this in this neuron or neural node, the weights are basically summed. The input is summed by kind of linear weights, and then they perform this, they operate it on the function sigma. Okay, so the sigma z is represented by this 1 by 1 plus e to the power minus z. Okay, so you have the value of z, and you can easily compute the value of sigma z, isn't it? So let's say the value is 0.98 for this node, and for this node the value is 0.12. Next, this 0.98 and 0.12 acts as the input to the next node. Okay, or the next layer. So I guess this is you have understood this. Now, why this non-linearity? Okay, ultimately the neural networks have to take a decision. What is this decision? The final layer, it takes a decision that whether the input belongs to class 1 or class 2, something like that. So that's why these kind of nonlinear functions are used to take this kind of decision. Okay, and basically they represent the nonlinear decision boundary as well. Okay, so that's why the neural network works. So now these 0.98 and 0.12 are the input to the next layer, and then the layer gets the output of 0.86, and this node in the next layer gets the output of 0.11, like that. Okay, so every time these values are changing. So what is changing? These weight values are changing, and as a result these outputs of the nodes are also changing. Okay, and ultimately the aim is that the network should converge. Okay, so that means that uh, and one thing is that uh, if you do the calculation, you can exactly determine the value of the output if you know these terms. Okay, so there is no ambiguity as such. Okay, but you see that these values depends on the weights and the biases, so the weights are trained accordingly. Clear? This is basically it is actually computed by using a matrix operation. Okay, because the inputs are a matrix and these weights are actually matrix itself. And also one thing is that these optimization or these computations can be done in parallel to speed up the convergence. So there are different kinds of activation functions, and depending on the position of the node, so we use different kinds of activation functions. I will come to that later. Okay, so the softmax layer is used in the final layer. Okay, so the aim of the final layer is to produce a probability map or probabilistic representation. For example, let's say I have three classes, so I will get an output 0.88, 0.120, like that, so that the sum of the values are basically 1, and also these values are within the range 0 to 1. Okay, so what does this represent? This term represents, this 0.8 represents that the network is 88% sure that the input is actually class 1, belongs to class 1. Similarly, this is the probability of class 2, class 3, like that. Okay, so ideally we want that one class probability should be 1 and the other class probability should be 0, isn't it? So the network tries to achieve that as well. Okay. Yes. Now here in this slide we define that how we set the kind of network. So let's say the image is of size 16 into 16. So we have 256 number of inputs, and these 256 inputs, they actually are fed to the neural network, and the final layer, it actually constitutes a softmax layer. Okay, and we, let's say that we have already trained the network and we want to predict what is the class belongingness of this image too. Okay, so finally the softmax layer gives you the output 0.1, 0.7, 0, 0, 0, 2, 0.2, like that. Now if you observe that here also the sum is 1. Okay, and we basically check that which probability is higher, which is the maximum. Here you see that the maximum is 0.7, that represent class 2. So the neural network will say that the network is 0.7% sure or 70% sure that the image belongs to class 2. Okay, but this kind of and now basically we compute the classification accuracy of the network and determine and see that how the network performs. Okay, so we are basically choosing these parameters w1, b1, w2, b2, like that. Now in most of the cases what has happened nowadays is that people have observed that if I use this kind of networks for other tasks also, let's say that I train a network for handwritten digit, and I want to predict a printed digit using the same network, because you see that there is handwritten digit and the printed digit, they are basically somewhat similar, isn't it? So the network trained from handwritten digit classification will also work for printed digit classification. Okay, so this kind of approach is called transfer learning. Okay, so that means the learning is transferred to some other task. We have trained the network for handwritten digit, and we will use the network, same network, for printed digit classification. Okay. Now it is very difficult to prove this kind of mathematics behind this optimization and all, and so we will not go into that detail of the mathematics, but you basically have an idea, I guess, isn't it? So in the training phase, what you say, we give this kind of images and we give this kind of labels. So we say that, look, this image represent 5, this image represent 0, this image represent 4, like that. Okay, it's all and good, but the problem is that we want a lot of images, isn't it? Merely, let's say, 7 images per class will not work. You need at least 100 image per class, so that the network can identify the exact features from this kind of classes, and then they perform the prediction. Okay. So previously I had mentioned about the loss function or the cost function. Okay. So whenever we are talking about neural network or deep learning, everything ultimately boils down to optimization. Okay. So this neural network set a lot of parameters. You have to set the parameters. What should be the exact value of the parameters, or the optimal values of the parameters? So that is determined by this kind of optimization kind of formulation. Let's say that the neural network has parameter theta. So the theta includes this W1, B1, W2, B2, WL, BL, dot dot dot. Everything is inside this from theta. Okay. So we have to get the exact value of theta. How do we do that? So we perform training. In the training, we know that what should be the output for this image that is belongs to class 1. Because it is class 1, the output should be 1000. Okay. But for a particular specific theta, it may be 0.2, 0.3, 0.5. So the difference between this and the ideal output is the cost function. Okay. Why does this cost function differ? Why is it not the actual one? What do you think? Yes. Any guess on that? You understand my question? That let's say that I got this value 0.2, 0.3, dot 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 0.5, but the ideal value should be 10000. So why do you think that we are getting 0.2, 0.3, dot 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 0.5 rather than this value? What do you think? Yes, any guess? Yes, it is not the value differs because we have not chosen the optimal value of theta. When we build the network, we start with some random value of theta, isn't it? How do we know that what should be the actual value of theta? There was no way of understanding that. That's why we start with this value, and then basically we compute this loss function. So the loss function itself depends on theta. So we represent it as a function of theta, L theta, isn't it? Now we can compute L theta in different measures like Euclidean distance or cross entropy or other kind of uh, criteria. Okay, whatever be the criteria, our aim is that we have this overall C theta, which is the loss function for all the inputs, all the training samples. We simply want to minimize this C theta. So we vary the parameter theta so that we get the optimal value or the minimum value for C theta. Clear? So you see that because C theta is also a very high dimensional, so the optimization surface looks like this. Okay, so we use different kind of optimization algorithm to get to the optimal value. Okay, there is the most popular one is the gradient descent algorithm, and apart from that there is the Adam optimizer that is becoming famous nowadays. Whatever be the value, we are not going into that detail. So our aim is that we have to get to the optimal value of theta. So but this error surface can be very complicated. Okay, but still we can get a fairly good approximation of theta if we use the proper algorithm and the proper loss function. But it's not very straightforward as such, because you see that there can be multiple minima. Okay, so once you reach this one, this minima, so the algorithm will understand that we have obtained the global minima, but it's not the global minima, that's that a local minima. So there is this problem, but there are some way arounds as well, so I am not going to go into details because this is more or less mathematical. And one more thing is that mostly the samples are trained using mini batches. Okay, so that means let's say I have 1 lakh samples. I do not feed all the samples to the same at the same time. I divide it into some batches and then I feed it to the network. So because the network needs to run on some kind of GPU or some kind of processor, so the processor has a limited capability. So that's why we use this kind of mini batch. Okay. Now, basically, we perform the optimization using back propagation algorithm. So that means the error is back propagated. So the idea is like that. We can exactly know the output of the final layer, but we do not know what should be the exact ideal output of the intermediate layers, isn't it? So we back propagate the error. So that means that if the error is like this, so what should be the value of the intermediate layers? So that way we determine the weights and the bias terms. Okay. So now I want your feedback whether you are able to get the overall idea or is there any doubt? Okay, there are many softwares nowadays available like PyTorch, TensorFlow, Theano, and other toolboxes as well, several toolboxes. Yeah, so you can simply use these kind of toolboxes to perform your analysis or learn about deep learning and machine learning, deploy some models. Okay, there are several resources as well, so you can go through that. So I recommend that you should start with TensorFlow examples or Keras examples. Okay, so Keras is actually a machine learning or deep learning library. So it has a several examples, and they have also explained it. You can basically even the newbies, they can also start implementing this. So this is all about the back propagation algorithm, which is actually you can see that the error, I know that what should be the output of the final layer, and I also know that what is the actual output of the final layer. So I can compute the discrepancy or the difference. Now, why this difference is happening? This difference is happening because the connection from the previous layers are not the output from the previous layers are not correct, isn't it? So you see that the output of the previous layer is weighted sum, and we get the output of the final layer. So the error are also weighted summed. Okay, so that we know that what should be the output, what should be the contribution of the next layer, isn't it? So that way we compute the overall weights and the bias terms. So the error is essentially back propagated. Okay. So this idea allows the neural network to be trained from the training samples. Clear? Now you see that we say that the deep neural networks are a collection of neural networks arranged in a large number of nodes and layers. But how many layers should be there? And how many nodes should be there in each layer? There is no formula as such. For example, you can see that there are two kind of networks. First one is the shallow network, and second one is the deep network. Okay. In the shallow network, let's say there are two layers. So this blue cover, this is one layer. This is the second layer. In the layer one, let's say there are 10 nodes, and layer two there are only 2 nodes. Okay. So all layers are actually in connected in between. So this is one way to build the deep neural network, the neural network, or we can go in another way. So where we have also 3 layers, but each layer is having 2 nodes each. Okay. So there are several ways. There are several ways to build a neural network. But you have to remember one thing, that if the number of nodes in the final layer should be the number of classes. Okay. For example, if there are 2 classes, you should have 2 layers in the output layer. Okay. So this layer will represent the probability of class 1, and this layer will represent the probability of class 2. But you can design in infinite number of ways. So which one is better? So the first one is basically a shallow network, which means that the network has relatively smaller number of layers. Okay, the number of actual neurons can be high, but the number of layers is small. But in case of deep neural network, you have a large number of layers, and the number of neurons in each layer may be small or may be large. But researchers have seen that the deep networks are better at different tasks like classification, regression, or object detection, or other tasks. Why is that? Because you see that each layer basically learns something new, some very specific features, and they are constantly interacting with the next layer. The next layer is also feeding the information to the subsequent layer, like that, so that they form a kind of a very abstract, they get some kind of very abstract representation, and these representations are very powerful, and also they identify this kind of non-linear decision boundary. Okay, so that's why deep neural networks are preferred over the shallow ones. So here we show some specific neural network architectures. Okay, So the left one, it is actually a two-layer neural net. When we are talking about two layer, so we are including the output layer also. But you can also say one hidden layer neural network. So in neural network, we have input layer, output layer. These two are must. Okay, the input layer represent the number of dimensions of the input. The number of nodes in the input layer should be equal to the number of dimensions of the input. For example, in that image classification task, we had 256 numbers. So the input layer contains 256 number of nodes, isn't it? And the output layers represent the classes. Okay. And in between there can be one hidden layer, two hidden layer, or any number of hidden layers. Okay. And the connections may be fully connected, or other kind of connections may be there. So this is how this neural network basically architectures are formed. Now, as I had mentioned that the main idea why of the neural network is that the neural networks can realize any arbitrary function. Okay, so that means it can exactly identify the mapping between this input and output. We did not talk about the activation function. So you see that the activation functions are used to represent some sort of nonlinearity or some sort of thresholding. Here, popularly, these 6 activation functions are used. This is the sigmoid one, which is represented by this equation. Okay. So let's say, for example, let's say that the x value is 0. What should be the y value? Sigma x value. So if we put x equal to 0, you see e to the power 0 is 1. So the sigma x is 1 by 1 plus 2, that is 0.5. And if the value of x is very small or very negative, highly negative, then you see that this value will be almost 0. And if the x value is high, okay, then the value will be 1. So that means that if the value of x is very slow, very highly negative, then the phi x value is 0. And if it is very highly positive, then it is 1. So it acts kind of a switch or some kind of a threshold. Similarly, this tan h function also performs this. You see the characteristics is almost similar. Only thing is that the tan h is more sharper. And also sometimes we use ReLU, so which is represented by max of 0 and x. So if the value of x is negative, then we get the let's say it's negative 10. Okay, so the value will be 0 because it's a max operation. So we only retain the positive values. Similarly, we have this decay ReLU function, which is represented by this max out and ELU. Okay. And most of you are actually interested in working in some sort of image processing in metallurgy or other applications. So the way this image processing deep neural network work is somewhat different than the fully connected layers. Okay, so here we have the concept of convolution. So in images, what happens is that the image has kind of spatial structure, so that the pixel values of the neighborhood pixels are very much similar, isn't it? Of course, there is some edges or something. This convolution neural networks or the convolutions operation, it actually attempts to perform this, extract this kind of spatial information. What happens here? Here basically a block is basically slided. Okay. For example, let's say that you have a 5 and 5 into 5 block, and you compute a weighted average of this thing. Okay. So you get a single value for this 5 and 5 convolution. You slide this convolution kernel, this is called the kernel, over all over the image, and you get a kind of a collection of values or a matrix. So if you put this kernel at this position, you have a particular value. Now you are sliding this, and because of this, you have a kind of matrix. isn't it? So that's why the convolution layers, they use a lot of kind of convolution filters to get some activation maps or the feature maps, isn't it? These feature maps are very much useful for classification, object detection, or other kind of tasks. So in case of image classification task, we use convolution. As this convolution, I have shown what is convolution, and then they apply a ReLU or some kind of activation. I have shown what is this ReLU, and you get some output. This output is again some convolution operation is performed on the output, and then there is some ReLU operation. Like that, we get some final features. Okay. For example, let's say that there is a classification problem where we have to classify some images. So these are the features that the neural network extracts. Okay. As you see that this, we do not know that what these features exactly represent, but the networks achieve very good performance. Okay. So I think that you have a basic idea about some deep learning methods for image classification or supervised learning. Okay. So any doubts from the so far? Hello. So I am thinking that I can show a brief demonstration of this deep neural network so that you can also those who wants to perform the practical, they can also start.
So,
Okay.
what is
Yes. Any doubt? Yes.
activation function? What is it, sir? And how do we use it?
Yes. So basically, so what we do in neural network is that we sum up. Let's see. Let me go to the slide. Yes, you can see in the slide. So this is what happens inside a particular node in a neural network. So the inputs A1 to AK. So these are actually weighted by these weights W1, W2 like that, and we add this value B. So we get the value Z. Now we apply the activation function on Z. Okay, so these activation functions are some sort of non-linear functions. Okay, so this Z is nothing but a linear weight of the input. So it represents a kind of straight line, but you see that these straight lines cannot represent the actual classification decision boundary, isn't it? Yeah. For example, you see that the decision boundary is not linear, so we cannot represent it by a straight line. So we need some sort of non-linearity. So that non-linearity is introduced by this activation function sigma. Okay. For example, here you see the sigma is like this. If we use the sigmoid function. Okay, here this is not a linear thing. This is a non-linear function. Okay. For example, we can have other activation functions like tan hyperbolic or ReLU or other thing. So this activation function is used to represent some sort of a non-linearity on the data. Okay. So is it clear?
Yes, sir. Thank you, sir.
Okay. Any other doubts? Okay, so now what you can do is that I am sending one link in the chat. So you can open the link and you can start the implementation. Sir, can I share some message in the chat?
Yes, yes, you please go ahead. You can share.
I'm not seeing the option.
Or in a QA tab, you can send something.
Okay, okay. So nowadays, basically, there are some online platforms. Yes. So nowadays, there are some online platforms where you can run your machine learning model or do some sort of analysis. Okay. So here you do not exactly need any specific software. Rather, if you have the internet, that is sufficient. Okay. So there is this. Let me share the screen also. So you can see the Google Chrome tab, I think.
Yeah, it's
Yes,
visible.
yes. I see the theoretical part is one thing, but most of the people are also concerned about the practical implementation and all. So it will be good if I can show you some sample examples. So you see that there is this kind of uh, Keras is a kind of software or Python toolbox which is used for machine learning or deep learning implementation. Okay, so you simply go to this Keras, this link which I showed, and then you open View in Colab. Okay, so Google Colab is a basically platform, is a Python platform provided by Google. So where the codes are implemented in the Google Cloud. Okay, so if you open the Google Colab, okay, so you will see these codes and all. So here basically I can run some demonstration of image post classification using deep learning models. Okay, so everyone able to open this link, Google Colab link? You do not need any software. You can simply open this thing and you can run the code. Okay, or you can understand how this works. So basically here we will be trying to implement a image classification problem. Okay, so you see that in the first setup, so there are some libraries for image classification or deep learning rather. So there is this TensorFlow library, this TensorFlow.keras library. So these things you need to import. So first we import TensorFlow STF, then from TensorFlow you import keras, and within keras also there are some specific facilities you need to import. Okay, so you can simply click on this run cell button. Okay, so if you click on this run cell button, you will be able to execute the codes. Then we will download some data sets from some online link. You see the link is given there in https download microsoft dot that. Okay, so you try to run that cell also. Okay, you have done that, or if you face any problem, please let me know. Next we have to unzip these images. Okay, and we have to create it in different subfolders. So we run this next two cells as well. Now what we are going to do is that we are going to format this kind of data. So there is this code also has some comments. Okay, so there are some corrupted images as well, so it is actually filtering out that, but that is a different thing. You don't have to be concerned about that. So you run this cell as well. So this cell in filter out the corrupted images, you run that cell. Have you completed? Yes. Okay. Then we are going to create the data set. Is you run this cell called generate data set. Okay. So there is this function called tens.tf.keras.utils. So it actually extracts this data sets and divides the data set into training set and validation set. So you see that these images are of size 180, 180, and we divide it into batches of 128. Okay. So this function will do that only. So try to run this cell, and once you have completed that, then next what we are going to do is that we are going to visualize some of the image data. So you should run this cell, visualize the data. Okay, so here what we are doing is that there is a library called matplotlib.pyplot. So it is used for different kind of plotting or image so representation. So we show some of the sample images from the data set. You can see some are cat images, some are dog images, like that. Okay, we have to classify these images. This is our task. Now you see that in this data set there are basically uh, uh, there are 23,000 images, but the deep neural networks require a lot of data. How do you get a lot of data? Maybe you may not have originally have all a large number of data, so you can always do some sort of data augmentation to create more data from the existing data. So you run this cell data augmentation, also run the next cell, and you will understand what we mean by data augmentation. So the original image is this one, and the augmented other images are augmented images. What is happening here? You see this original image has been rotated in this case, and also there has been some sort of translation. That means the images are shifted or rotated or something like that. Even if the images are rotated, it still represent the same class, isn't it? So this kind of data augmentation increases the number of samples. Okay. Now we have to make the data into the same format. So ideally, originally the images are of 0 to 255 range. Okay, so that means the pixel values vary from 0 to 255. But to make the learning better, it will be better if we rescale the values to 0 to 1. So first of all, we perform this kind of pre-processing. Okay. So we standardize this data. So you run this model. Okay, so we are configuring this data. Next, we are going to use a kind of deep neural network to classify the images. So I have shown you I have explained about convolution neural network. We are going to use some sort of convolution neural network to perform the classification. So we have defined the model here. So def make model, you can see here. So this is a kind of function, or in this function we define the input shape and the number of classes. Okay. So that means what is the shape of the input image? Here is 180, 180, and how many classes are there. Depending on that, we develop the model. Okay. So the model includes uh, convolution layers, batch norm layer, activation function, and other kind of things. We are not going to this specific, so you can build your own model or you can use some other model to perform this classification. So how this model works is here basically they have given the model details. First one is batch normalization, then max pooling 2D, like there are a lot of layers. Okay. Now we are going to do the training process. So we are going to train the model. So we have used 25 epochs. In these 25 epochs, the model is going to perform the optimization and then get the tune the model, and this trained model will be used to basically perform some sort of inference on some unknown data. Okay, so what we have done is that we have basically used this data set, and we have built our own model like this model. Okay, and now we are training the model. Once the model is trained, we will be able to know what are the optimal value of the parameters for this network and for this data set also. Okay, so now basically the optimization is taking place. Okay, so we have chosen 25 epochs, and here the model parameters are specified. Let's say that model compile. So the optimization method uses Adam optimizer with a learning rate of 1 into e to the power minus 3. And then we have used the binary cross entropy loss function, and we have used the accuracy as a metric. Okay, so now maybe we will not understand everything, but I suggest that you search these functions. Okay, you simply go to Google and search model.compile and understand what this model.compile does. Okay, and what are the input output arguments of this. Okay, so once you build a model, then you have to compile that model. That means the model has different parameters. You have to specify these parameters.
Excuse me, sir.
Yes.
Sorry to interrupt you, sir. Actually, and the next speaker is waiting. Can you make it faster?
Yes, yes, yes.
No.
So yeah, so basically because you have the kind of notebook, you can always do run this thing. Okay, so here the optimization is taking place, and then you can, if you run, once this is training is completed, then you can run inference on the new data. Okay, so for example, you give this image a particular image. Okay, and then what we try to do is that you try to predict that whether this image belongs to dog class or cat class or some other class. Okay, so this optimization will take some time, don't worry, but once that finishes, you run this code, this section, and you will be able to get the prediction for any input image. Okay, so I hope you got a good starting point on how to implement deep learning or image classification or other tasks. Okay.
Sir, I have a
Yeah.
question.
Yes. Yes. Yes.
You have shown data augmentation for images by
Yes.
changing the angle or changing the contrast, right? So can we do the same for numerical values? I mean, like we have a composition of certain materials and label with certain output. So can we augment the data for that?
Yes, yes, obviously, but this should not be very straightforward because I do not have that much expertise on this metallurgy. But you see that in case of image, it is straightforward. You change the angle and do the translation and all. So you have to think that which kind of perturbation will not affect the class level. Okay.
Okay. Thanks.
Any other doubts and other queries?
Participants, if any queries, please ask.
So if there is no other query, I think I can conclude the session.
Yes, sir.
Okay, okay.
Thank you, sir, for your useful and demo presentation.
Thank you.
So
Thanks
it will be
everyone for
useful.
your time and effort. Yeah. Okay.
Yes.
Okay
Thank you,
then,
sir.
sir. Yeah. Thank you. Bye.
Bye, sir.